In this video, we are going to be discussing the reactions that diene undergo, starting with electrophilic addition. Now, we first learned in first semester organic chemistry that whenever you have an alkene in the presence of HX, which is going to be any type of acid, it could be HBr, it could be HCl, we're going to have an addition reaction in the Markovnikov way, meaning that the carbon atom that has the most hydrogen is where we're going to incorporate the incoming hydrogen, and then the carbocation, as long as there's no rearrangement, is going to be attacked by the bromine or the bromide ion, in this case because we're reacting with HBr, that anion is what's going to attack our carbocation, and then in this reaction we're going to make an alkyl halide. Understand that if you have a diene, and as you can see we have here the most stable, the S transdiene, in the presence of HBr we are going to be making two products, okay? And now we're going to discuss why specifically is that we make two products. So understand that if we go over the mechanism of S-transbutadiene undergoing this addition reaction, this halogenation reaction, what we know is that at this point, because we have this diene and the protonation happens, we know that if I label the carbon atoms that are in that corner, this one, and I'm going to label the other one in orange, and then if I see it and I relabel the product of that first step of the reaction, again, because this is a Markovnikov addition, the hydrogen is going to go to the carbon with the most hydrogens. Now, that being said, as you can see, we are going to be making an allylic carbocation. Now, this allylic carbocation is going to have a resonance stabilization. So as you can see, we make two allylic carbocations. So this is the first one, and then the second one is just the resonance structure. So we make a second allylic carbocation. Now, the formation of these two allylic carbocations is what results in the two different products that we have. Understand that in this reaction, we do not have specifically a formation of a primary carbocation, because remember that primary carbocation, it is not going to be formed. Remember, this is a Markovnikov addition. That primary carbocation is also not resonance stabilized, because remember that is sitting next to an sp3 carbon, and then resonance structure, that hydride shift, will not be occurring. So, taking into account that these two allylic carbocations are going to be formed in the molecule, in the next step of the reaction, you can see how each of those two allylic carbocations then can be attacked, in this case by the bromide ion, and that's where we get what is called the 1,2 addition product and the 1,4 addition product. Now, understand that if we have Br2 added to a conjugated system, we also have that dibromination or dichlorination happening at the 1,2 addition and the 1,4 addition. But again, it comes from the same idea, that in this case there's going to be a resonance stabilization that is going to be happening, and that's why we have the two addition products. Okay, to understand a different example for that 1,2 and that 1,4 addition, I'm going to take one of the examples from the textbook. Let's say that we have to predict the product of the following reaction. I should say products, because there's going to be multiple. So let's say that we have the following cyclic diene. And we are going to be reacting it with HBr. And we're trying to determine what are going to be the products of the reactions. Now, understand that in this system, because if I decide to number the carbon atoms here specifically, we are going to be numbering this as 1, 2, 3, 4 carbon atoms. So understand that here we don't have symmetry within the diene. So the area of 1 and 2 and the area of 3 and 4 are different. Okay, so each one of them are going to be creating, okay, products. And let's illustrate that. So I'm just going to redraw the molecule in the bottom. So I'm going to redraw my cyclic system. And in the first step of the reaction, I'm just going to be focusing on the double bond of 1 and 2. So if this is reacting with HBr, let me just redraw HBr. If this is reacting with HBr, and this is grabbing onto the hydrogen, breaking the hydrogen-bromine bond, then understand that when I redraw this molecule, carbon number 1 is going to receive the hydrogen. That means that carbon number 2 is going to have a carbocation. Okay? This carbocation is going to have a resonance structure. So I'm just going to put it here in brackets, which for this, that double bond is going to move there. Once that occurs, then we're going to have between, let me just relabel this. This is carbon 3 and 4. This is 1, 2, 3, and 4. 1, 2, 3, and 4. So, as I mentioned before, because now that I have the labels on the molecule, the incoming hydrogen bonded to carbon number 1 because it already had the most hydrogens. Remember, this is a Markovnikov addition. That means that carbon 2 is going to receive the positive charge. Once that occurs, again, that is one of the first ones, allylic carbocations. Now that we have that allylic carbocation, the double bond that exists between carbons 3 and 4 is going to go and move to carbons 2 and 3. That means that carbon 4 is now going to receive the carbocation. So this is the second allylic carbocation. So when that occurs, I'm just going to erase now that blue arrow that I utilized for the carbocation. Br minus, which was generated in the first step of the reaction, can attack both of those allylic carbocations, and we're going to form two products. So you can see we're going to form the product in which carbon 2 gets brominated, and we're also going to form the product where carbon 4 is brominated. So let me just write the products of those two down there. Now, if the carbon that does the attack, the alkene that does the attack is going to be 3 and 4, I'm just going to write it in the bottom. Let me redraw the molecule. Let me relabel the carbon atoms. 1, 2, 3, and 4. If the alkene that proceeds to get protonated is the one between 3 and 4, then understand that at this position, we can have a carbocation form here, okay? Because at this point, 3 and 4 have the same number, okay, of hydrogens. So the proton can happen here, okay? Then this allylic position can have a resonance stabilization. Let me just relabel those carbons. This is carbon 1, 2, 3, 4. If now we move the carbon-carbon double bond from 1 to 2 to 2 and 3, then the carbocation is going to specifically be on carbon 1. Let me relabel the carbon atoms. And once that occurs, understand that specifically we're going to form the following compounds after the bromination step. So we're going to attack the carbocation on 3. We're going to attack the carbocation on 1. So we're going to produce the following molecules. So understand that even though at first you look at these two molecules and you may be thinking, oh, we have actually 4 products for the reaction, you can observe that specifically if we look at the molecule that we have drawn in the next step, okay, they actually are going to be equivalent to one another. So these 2 products, so one of the things in which you can do that is just by naming the compounds themselves. But these 2 products are going to be equal to one another. So in this reaction, we are forming 1, 2, and 3. Because in this last molecule, those 2 compounds that are written are going to be the same. So understand that whenever we're doing the predicted products in this molecule, be careful with the number of products that you represent at the end of the day, just because some of them can be the same. But in addition to that, take into consideration that whenever we are doing this, specifically when we were doing the attack between carbons 3 and 4, one of the things that you have to take into consideration is that because we are doing a particular addition to that carbon-carbon double bond. Remember that the intermediate that we're going to be forming is allylic in nature, because that's going to be the most stable one. So in this, understand that that's why the proton was added to carbon 4. So in the second case, it was added to carbon 4 and not to carbon 3, and creating that carbocation on number 4. Okay, so understand that even if you illustrate that that is another product, that product is actually going to be the same one as this one. Okay, so just try it at home. Continuing on with the concepts of chapter 16, understand that there's actually thermodynamic and kinetic controls when it comes to the 1,2 and or 1,2 versus 1,4 additions to dienes. So one of the things that is known is that the ratio of 1,2 versus 1,4 addition is highly dependent on temperature. It has been observed in the laboratory that when this reaction is ran at 0 degrees, there's going to be the presence of the 1,2 adduct more in the product compared to the 1,4. Now, if the reaction then is heated to 40 degrees Celsius, as you can see, there's going to be the production of a higher concentration or a higher number of moles of the 1,4 adduct. So if we want to illustrate why does this occur in terms of the reaction, understand that we can actually visualize this through an energy diagram. And when we look at the energy diagram between the two, understand that the formation of the 1,2 adduct is going to be faster. What does that mean? That specifically after we have that intermediate form, which I'm highlighting here in blue, see how the activation energy of that second step of the reaction it's lower. So that's why the 1,2 adduct is going to happen. Now, the 1,4 adduct is actually more stable. And because it has a higher activation energy compared to the 1,2 adduct, it is actually thermodynamically favored. That's why when we're increasing the temperature, we actually see more of it in the product of the reaction. Now, that 1,4 adduct is more stable, okay? And if we think about it, when we compare the 1,2 adduct to the 1,4 adduct, that stability actually is also due because the 1,4 adduct is more substituted in terms of the alkene. And even though specifically here we're not recalling the Sicev rule, that's one of the rules that you guys learned previously when you were doing elimination reactions. Now, that being said, I am not suggesting that this is a Sicev rule argument, but it does relate in a way to the Sicev rule, just saying that the more substituted alkene is the one that it is more stable. But again, the stability of alkenes in elimination reaction, that's what's related to the Sicev rule. In this case, it's just the presence of more substituted, which is a different argument for stability. So that being said, at higher temperatures, the formation of the products is actually equilibrating, okay? The reaction is under thermodynamic control. And that's why the product of the reaction that is more stable will be the major product of the reaction. Now, remember, the 1,2 adduct forms faster. And when we think about why that is, it is presumably due to the proximity effects, okay? So one of the things that we can look and take into consideration is that whenever that 1,2 adduct is happening, as you can see, we have the formation of that allylic carbocation on carbon 2, and this is just the way that the diene was numbered. Now, because the bromide ion is going to be closer to the C2 compared to the C4, it is thought that that is why that's going to be happening at lower temperatures, okay? So also the reaction is going to be under kinetic control. that reaction, understand that it is reversible, and the product that forms the fastest is the one that is going to be the major product. So remember, when it comes to the 1,2 versus the 1,4, it's going to be controlled by temperature. The lower the temperature, the more favorable is going to be the 1,2 adduct. But if you have higher temperature, then the 1,4 adduct is going to be the most stable product.